Hi guys. So again, we are going to do some more trig identities. So there's really not a lot of new content today. The thing that's going to be really different from last class is just a couple different strategies we didn't see, and you'll see a lot more practice problems that use these two Pythagorean identities that we didn't do as much last class. So quick refresher, again, what's written here is everything you'd be given for a quiz. But just a quick refresher on what these are. 1 over sine is cosecant. 1 over cosine is, secant. 1 over tangent is cotangent. 1 over cosecant is sine. 1 over secant is cosine. And 1 over cotangent is tangent. Sine over cosine is tangent. And cosine over sine is cotangent. The other thing I want to make sure we know how to do is how to rearrange these identities. So what I mean by that is taking this original. Let's look at the 1 plus tangent squared. If I subtract tangent squared from both sides, I can rewrite this identity as 1 equals secant squared minus tangent squared. I could also rewrite it by subtracting 1 from both sides, and I would get tangent squared equals secant squared minus 1. Same thing on the bottom one. I could subtract cotangent squared from each side, or I could subtract 1 from each side. So these are the different ways that you could write these expressions. Again, you'll only be given these 3, but you need to be able to rewrite them in the forms of the other ones. All right, so let's look at some examples. So one strategy we didn't do a lot of last class was factoring. So if you have 2 terms, remember the terms are the things that are added and subtracted. So this has 2 terms to it. Both terms have a secant squared. So I'm going to take that secant squared and factor it out. So if I take secant squared and divide it out of secant squared, that leaves me with 1. And if I divide it out of the sine squared secant squared term, that leaves me with sine squared. Well, now if I look at my Pythagorean identities, 1 minus sine squared is cosine squared. Secant squared is the same thing as 1 over cosine squared. Your cosine squareds cancel out, and you get 1. All right, the next one, it'll be pretty easy if you look at those Pythagorean identities. So look back up at your Pythagorean identities. 1 plus cotangent squared is cosecant squared. Well, now we can rewrite this. This is cosecant squared divided by secant squared. Let's write each of them in terms of sines and cosines. This is 1 over sine squared. This is 1 over cosine squared. When we divide, we flip our fraction. That gives you cosine squared over sine squared. Cosine squared over sine squared is cotangent squared. All right, C is very similar to what we saw the first day. We're going to need to combine these fractions together with a common denominator. So this left fraction has a denominator of sine times cosine. That means the right fraction needs to get multiplied by cosine top and bottom in order to have that same denominator. So when I do that, the first fraction doesn't change. The fraction on the right becomes cosine squared, and the denominator is now sine cosine. That denominator does not change, but we can go ahead and combine them together. Well, now we can use those Pythagorean identities. 1 minus cosine squared is sine squared. Remember, sine squared is just sine times sine. So if you have a sine at the bottom, that will cancel out with one of your sines. That leaves you with sine over cosine, and sine over cosine is tangent. Very similar in D, but D is going to be a little bit messier on the algebra. So we're going to multiply each side by the denominator it doesn't have. So the left fraction needs to get multiplied top and bottom by secant plus tangent. The right fraction needs to get multiplied by secant minus tangent. So what's going to happen here, if I actually do, I'll do it over here on the side so you guys can see it, and I'll erase this here in a second. If I do secant plus, let me give myself some more space. If I do secant plus tangent times secant minus tangent, if I were to actually multiply this out, this is a difference of squares. The reason this is nice is because our middle terms are going to cancel out. It's going to be a lot easier for us. So I'm going to go ahead and show you the whole step here, but in the future I'm probably going to skip the middle step. Secant times secant is secant squared. Secant times negative tangent is going to be a minus secant tangent. Tangent times secant would be plus tangent secant. And then I would have minus tangent squared. Well, like I was saying, it's a difference of squares because those middle terms will cancel out. One of them is plus and one of them is minus. So all that leaves me with the denominator is secant squared minus tangent squared. What makes this even easier is if you look at your Pythagorean identity, secant squared minus tangent squared actually is something. So check back at your identities and you'll see that secant squared minus tangent squared is just 1. So what all of that means is that this left fraction, when I FOIL that whole bottom out, it's actually just 1. On that right fraction, if I multiply that whole bottom out, it's just over 1. So I'm going to go ahead and erase that foiling. So now all I have to do is combine like terms. I have secant plus tangent plus secant minus tangent. Plus and minus go away. I'm left with 2 secants. When you add secant together, it's a secant plus a secant. You get 2 secants. It's not secant squared unless they're multiplied. All right, E is an example of why these trig proofs can be hard. You may think, hey, let me get a common denominator and combine these together. That is actually not going to be the fastest way to do this one. Now you can get to your answer, it's just going to take a lot of extra work. So what I'm going to do instead is show you guys a little bit of a shorter way to do this one. I'm going to rewrite that first fraction as sine x times 1 over cosecant. That is the same thing as that other fraction. I'm just writing it a little bit of a different way. I'm going to do the same thing with the other fraction. Okay, this is the same thing, just written a different way. The reason I'm writing it this way is because 1 over cosecant is the same thing as sine. And then 1 over secant is the same thing as cosine. Well, sine times sine is sine squared. Cosine times cosine is cosine squared. And sine squared plus cosine squared is 1. That's one of your Pythagorean identities. All right, F is another one where we'll use fractions. This is one you might be able to try on your own, so pause the video, try this one. Okay, I'm going to rewrite everything in terms of sines and cosines. That's a really common strategy that's helpful. Cotangent is cosine over sine. So now that's cosine squared. So in order to add these together, I need to get a common denominator. So I'm going to multiply the left fraction by sine. So that's going to give me sine squared over sine plus cosine squared over sine. Now I can add the tops together because I have a common denominator. And we know that sine squared plus cosine squared is one of our Pythagorean identities. Sine squared plus cosine squared is 1. 1 over sine is cosecant. All right, these next two, we're getting into some of the harder questions now. These are going to involve factoring. Now, it looks confusing in the way it is, but remember, cosine of x is kind of like its own variable. So at the very top here, we're actually going to factor that. And that is very similar to trying to factor something like this, which is something you probably saw in Algebra 1. This is actually a difference of squares. Now, it's been a while since we've done that, so in case you don't remember, a difference of squares is something like this, where there's two terms, you know both square roots, and there's a minus in the middle. The way that factors is into x plus the square root and x minus the square root. So x to the fourth minus y to the fourth, let's start a little simpler. If this was x squared minus y squared, it would factor into x plus y, x minus y. So same idea, but instead of being squared, the original problem is to the fourth power. So I'm going to take the square root plus the square root and the square root minus the square root. So that's how this would factor if it was just regular variables. We're going to do the exact same thing, except we're going to use, sorry guys, we're going to use cosines and sines. So this would factor into cosine squared plus sine squared and cosine squared minus sine squared. And now, once we're able to get past that first step, it's actually not a very hard problem. The first step's the hardest part. Because now you'll see that this entire factor can cancel out with that whole factor, which leaves us not only with just cosine squared plus sine squared, but using your Pythagorean identities, cosine squared plus sine squared is just 1. So that whole thing is just 1. All right, let's try h. Very similar concept. We're going to factor the top, and we're going to treat it as if this were just regular x squared minus 2x plus 1. You all know how to factor x squared minus 2x plus 1. Okay, that factors into x minus 1 times x minus 1. Same thing, except instead of x, it's cosine. So this is cosine x minus 1 times cosine x minus 1. All divided by cosine x minus 1. So guess what? Cosine x minus 1 cancels out. And you are left with your final answer. All right, so the last one on here uses a strategy we haven't seen so far. And this is one for a little bit of an extension for you guys. So if you want, you can go ahead and stop the video at this point, unless you really kind of want to push yourself and see some harder examples. This is actually a more of an example of a trig proof, where it tells you actually what the answer is supposed to be. What you have to do is show the work algebraically to get from point A to point B. So what we're going to do, there's a lot of different strategies you can use to figure this out. But actually, one of the easiest things to do is to do something called multiplying by the conjugate. So the conjugate is basically the same thing with the opposite sign in between those terms. You used this in 2 other places in your previous math classes. One was when you had something like this that you needed to rationalize. If you had to rationalize, you multiplied by that, top and bottom. That was the conjugate, because it was the same numbers, but the sign in between was opposite. The reason that you multiply by that is because, like we did earlier, when you FOIL it out, those middle terms will cancel out. So that's why we like to do this and why it's really helpful. The other place you might have seen this, on level might not have done this, but I'm pretty sure honors did. At least my classes did. What you would do is you would again multiply by the conjugate here. So you would multiply by 3 minus 2i in order to get rid of those things. Because again, it makes those middle terms cancel out. All right, so let's try this next one. So what I would do is I would multiply the top and bottom here by the conjugate, the same thing with the opposite sign. So I'm going to do secant plus tangent. And this is actually the same thing we FOILed out earlier. If you remember, the plus secant times tangent and the minus secant times tangent canceled out. So I'm actually not going to write those. I am going to have secant times secant, which is secant squared, and then tangent times tangent, which is tangent squared. Now at this point, go back and check your Pythagorean identities. Secant squared minus tangent squared is just 1. So this is just secant plus tangent, which is where you were trying to get to on your final answer. All right, so that is it really, guys, for notes on these. Really, the best thing you can do is work the practice questions. You've got to try these on your own to kind of see the different things that can happen to really get good at these. Just kind of watching examples may not help you a lot unless you try them on your own.